All right. If you got a problem, I'll solve it. So find solutions. Is x equals 3 a solution to 4x plus 10 equals 22? Well, let's check it out. Well, in this particular equation, the variable is x right here. There's only one variable and we are given its value. So they're saying x is 3. Okay, well, if x is 3, then this really reads 4 times 3 plus 10, which is 12 plus 10, which equals 22. And so the answer is yes. Is x equals 3 a solution to this? Yes, x equals 3 works. It makes it truly equal. Provide two values that are not solutions to the equation 4 times x plus 10 is equal to 22. Okay, just going to make one up here. Let's go 1. When x equals 1, that gives, okay, what would this be? 4 times 1 plus 10 equals 14, which is not 22. Let's go 0 style. I like multiplying by 0. How about x equals 0 gives what? 4 by 0 plus 10, which would be 0 plus 10, and that's 10, which does not equal 22. So here are two numbers, and by the way, those are just like the next two I thought of. There are infinitely many possibilities of values for that x could be that will not make this true. There happens to be this one right here that does make it true. Okay, so we found a solution, and we also found out that there are many that are not solutions, many values for x that are not. The difference between a number of dependents and 2 is 10. Okay, we better write this down. I'm going to call this D for dependence. The difference between the number of dependents and 2 is 10. Okay, so the first thing I did, maybe I should have read the instructions, huh? So, write down the equation and solve it. So the difference between a number of dependents and 2 is 10. Solve it. Well, it's 12. The difference between 12 and 2 is 10. So, and if you are an equation solver, well, to undo the takeaway 2, we would add 2 to both sides, or both amounts, and we would get D equals 12. Okay, so the number of dependents is 12. What do you put into a calculator to check this? Okay, so here we go. And what I'm going to have you do in this situation is for y1, we are going to put in the left side of the equation. But of course, your calculator doesn't speak in dependents. It doesn't speak in all kinds of various variables like t and v and w's. So we're going to have to put x minus 2 into y1, and we're going to put the right side of the equation into y2. Okay, and then we're going to graph this. So here we go. I'm going to go y equals, and let's see, where's x? Right here. X minus 2, and then I'm going to hit enter, and in y2 I'm putting in 10. Okay. And now I'm going to go to zoom, and I'm going to go down to 6 or hit 6, enter for standard view, which is 10 by 10. Uh-oh, they do not meet. So I'm going to actually zoom out. So zoom out and hit enter, and then hit enter again. It's asking you to center your zoom, by the way. Okay, so it zoomed out and it found this intersection point. Now what I'm going to do is this. Right above trace, you see calc. So I'm going to go second calc, and I'm going to go to 5 and find out where they intersect. Okay, it says first curve is blue, second curve is the red line, and sure, there's my guess, doesn't matter. There's the intersection. Okay, so it says at the intersection of these two lines, so this one being our left side of the equation and the red one representing the right side of our equation, where they meet, the x value is 12 and the y value is 10. So let's bring that back to, whoops, wrong way. Okay, what do you put into your calculator to check your answer? Draw the graph in the space here. Well, here's what we just did. We put x minus 2, which is the left side, into y1. We put 10 the right side into y2, and then we graphed it. We did have to zoom out, which is fine. Oh boy. It's hard for me to draw straight lines. Okay, this is a rough sketch. Something along these lines was our image. And right here, we did this. We did second trace, which is calculate. We went to the intersection, and we found out that they intersect when x equals 12 and y equals 10. Yeah? Okay, but here's what's up with that. This gave us our solution. So we were finding out when y is 10, or when this is meeting 10, how much is our value for x? Well, x was playing the role of d. So here, this is us saying, well, our d is equal to 12. So draw the graph, find the intersection point, and notice that really that meant the number of dependents was 12. So we were right. Use the table feature to check for equivalence. Okay, hold on. Back to the calculator. Whee! Okay, so now instead of graph, I'm going to go second graph, because that's the table. So second graph. And we see this. And remember, in y1, we put in the left side of the equals, which was d take away 2. And in the right, or in y2, we put in the right side of the equals. And now if we keep going down, we will find out when these are really equal. There it is. They are both equal to each other when x is 12. Okay, so our table can also find us solutions or intersection points the same when they are equal. So we can find equivalence through the table. Let's see. Put the table here. You betcha. So that looked like, I'm not going to put the whole table. I'm just going to put a right around where we found some values. So I'm going to go 10, and this looked like 8 and 10 at 11. 11 take away 2 was 9, and this was 10. At 12, we got 10 and 10. At 13, 13 take away 2 is 11, and we had 10. And we found the equality right here. Yeah? That's when both sides, the left side of the equal sign and the right side of the equal sign, were both actually equal to each other when x equals 12. So, yet another way to find our solution. So this is saying x equals 12, but that really meant the number of dependents was 12. That's a lot of dependents, by the way. Okay. The sum of $9.50 and the deductible is $17.25. Well, I'm going to call D the deductible. So, similar situation here. For the equation, so it says the sum. So, $9.50 plus, I'm going to call the deductible D, is equal to $17.25. And it says solve it. All right, well, how much do I need to add to almost $10 to get to $17? Well, in order to get from $10 to $17.25, I have to go up, what, $7.25? So I believe that our answer, without using a calculator, is going to be $7.75. But just to be super duper duper like on my toes, if I take away $9.50 from both sides, okay, let me quit the table. $17.25, take away $9.50, and yes, I agree with myself. So the deductible here, $7.75. What do you put into your calculator to check this? Well, similar pattern here. In Y1, we're going to put the left side. $9.50 plus, oops, not a D. Whoop. Can I make that into an X? We'll see. Yeah, sure. All right. Because remember, calculator doesn't speak in D's and W's and T's and whatnot. And in Y2, we're going to put the right side of the equals of the equation. And then we're going to go ahead and go back to our graphing calculator and do our business. So let's zoom here. I go to Y equals. What do we have? We actually have X plus $9.50. Or if you're like, no, that wasn't it. It was $9.50 plus X. And the right side was $17.25. Okay, I'm ready. Here we go. We're going to go zoom and go down to standard and hit enter. Okay, we didn't even get to see both of them, so we need to zoom out again. Zoom out, enter. Sure, why not? Okay, voila. So now we have a picture and we can find out where these meet by going second, calculate, go down. So use these arrows to go down to intersect, hit enter. Okay, first curve, the blue one, sure, hit enter. Second curve, the red one, sure, hit enter. The guess there, sure, hit enter. And it found our intersection. It intersects when X is equal to $7.75. Okay, so let's jot this all down. Okay, so our picture looked something like here, and it said x equals 7.75 when that happens. And that really means, I don't know why I put that in. I'm just going to write it. That really means that D, the deductible was $7.75. Yeah, because we replaced our D with an X, so now we're going to replace our X with a D for the deductible. Got it. Use the table feature. Let's try that again. So now let's go back to the calculator. And let's go ahead and go second graph to find our table. And let's see. Y1 is lower. Uh-oh. Look at that. So when x is 7, the left side of the equals was $16.50 and the right side was $17.25. And then when x is 8, the left side was $17.50 and the right side was less than that. So there was a switch over in between 7 and 8. But our table is only counting in whole numbers, so we're going to need to format that. So we're going to go second, maybe we should do table set. Do we really want our table to start at 3? Let's start our table at 5. That's a little bit closer. And instead of incrementing by whole numbers, well, we know we're going to have to increment at least by quarters because that's what our solution ended up. Let's suppose I put in here, let's go by tenths. Okay, so now I'm going to go second table. And notice that the x values are now going up by tenths. So now I'm going to hunt for when these y values are actually equal to each other. Man, that's still not good enough. Okay, so we needed to go, so second table set, we needed to go by 5 cents because it was quarters, it ended up being 3 quarters. So I changed it to going up by 5/100ths instead. I'm going to go second table. And I'm still going to look to see where they're equal. So here we are. Voila. So where the left side of the equality or the equation was $17.25, now is also showing it's equal to the right side of the equation, which was y2, and that's when x is equal to $7.75. So let's jot that down. What did we see here? We put in, oh, I don't need that. I need to draw my table. I'm on it. So x, y1, y2, and right above that we had what, 7.7, and y1 was 17.2, and y2 17.25. Then we had 7.75, 17.25, 17.25. Then we had 7.8 in the table for x. The y1 was 7.3. That's the the left side of the equals, and 17.25 was the right side of the equals, which told us right here this is where the left side of the equals is truly equal to the right side of the equals. So that's where this $9.50 plus the deductible is equal to $17.25. And so that shows us that happened when x was 7.75, or to give equality, but really that was a D for deductible here. Okay. Let's do it again. your bill is 2/3 of the original cost. You were charged $12. What was the original cost? Write the equation. We don't know the original cost. I'm going to call that C. So 2/3 of C, which is multiplication, is equal to 2/3 of the original cost is your bill. It's like okay. If you were charged $12, what was the original cost? Okay. So this is how much you're billed. And so if you're going to look at this as an equation, perhaps so I rewrote this immediately for part A, but really what I was thinking is this, if I call B the bill, I really was thinking B, and my is translated into an equals 2/3 of C. So my B was $12, my bill was $12, and this of became multiplication. Let's solve it. Oh, okay, well, here we go. You could actually do this different ways, but since this is being multiplied by 2/3, you could carefully divide each side by 2/3. Or if you wanted to, you could scale everything up by 3 and then scale everything down by 2. I'm actually going to scale it up, scale it down. Scale both sides of this equation up by 3. Triple this and we would have 2C. Triple 12 and we would have 36. Scale both of these down by 2 and we would have C equals, okay, scale 36 down by 2, I believe that's 18. Okay, and you will get the same amount if you actually properly do 12 divided by 2/3. But make sure you put in parentheses because otherwise it'll mess up the order of operations. So the original cost was $18, but you were billed $12 because you only paid 2/3 of the original cost. I don't know. It's a coupon or something. What do you put into your calculator? Let's do it. So here, the left side would read 2/3 x. The right side for y2 would read 12. And we would do the same business. So let's go to y equals and change what we have here. 2/3 and then times x. It doesn't matter if you actually put parentheses or a multiplication sign. Equals 12. Oh, I'm going to need to clear it. Equals 12. And I'm going to go graph. Maybe I'll have to zoom out. Maybe I won't. Okay, great. Now I'm going to go second calc. Go down to intersect. Enter, 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 enter. And it found it at x equals 18. Super duper. Okay, so it looks like here is a rough sketch of the image. That's where they met, and that happened to be where x equals 12. So the cost, because we replaced the cost with an x to use our calculator, cost, original cost, I guess we would call it. Oh, I'm sorry. X was 18 there. I just accidentally copied this 12. 18. Original cost, $18. Sorry about that. Use the table feature to do the same business. Okay. That's fine. Okay. I didn't change how the table was set And so it's still counting by 5/100ths. This could take a while. Yeah? Okay, so I'm going to redo it. Second table set. Start the counter at 7. Sure, because we're not there yet. Go up by 1s. Okay, and back to the second table. Here we go. Started at 7. Find where they're equal. There they are. They are both sides of the equation, the left side and the right side, are equal to 12 when x is 18. Okay, so let's get that on the page. X, y1, which was the left side, y2, which was the right side, and I'm just going to go a little bit above and a little bit below that. They were both 12 at 18, that's why we stopped. At 17, this was about 11.3, about. That was definitely rounded. At 19, this was rounded at 12.7-ish. And we notice that this is where the left side of the equals is equal to the right side of the equals when x equals 18. Okay, so x equals 18. Really, that means that the original cost was $18. Okay. The product of -5 and a number is -1.5. Okay. I'm just going to call the number n. The product of this. So the -5 times n is equal to -1.5. All right, we got this. Let's solve it. So divide both sides. Scale down by -5. Okay. -1.5 divided by 5 is -3/10. Okay, so if you take the product, whoa, I accidentally forgot a negative sign. Negative divided by a negative is a positive, and I definitely see that on my calculator I divided by a +5 instead of a -5. So careful with your signs. Okay, there we go. That makes sense now. If I have a -5 times 3/10, then I definitely get this. Or if I think about this a little bit differently, and I'm in debt 30 cents 5 times, then I'm in debt $1.50. Okay, so what I'm going to do here is I am going to quickly show the steps for this. Oops, but that wouldn't be -5x or -5n. Calculator doesn't have n. It has x. And y2 would be the right side of the equals. And the graph, okay, we would see, oops, on my color edition it would look blue and then it would look red. Okay, so rough sketch of what's happening is this is the image you would see. You would see -5x, this line, this is the left side of the equals. You would see this line at -1.5, that's the right side of the equals, and here where they intersect, that would give you x equals 0.3, but of course we had to replace n with an x, giving us the solution. Okay, and our table feature, if you're like, what's going on? I'm just very, very quickly doing this now. We would again have to adjust and do our table set, but at 1/10 this time. Okay, y2 is always going to be negative 1.5. So your table will definitely generate that. And that would be negative 1, negative 1.5, negative 2. Okay, so your table, if you entered these equations right and you changed your table setting to count by tenths, you should see this equality happen right here. Meaning that x equals 0.3, and of course this x represented whatever number we were looking for. Okay, and now you might have been thinking, like, why are we doing that? But now all of a sudden when we look at number 6, it's actually pretty easy to use a calculator to solve this. It doesn't say to use a calculator, but at this point what I want you to realize is that you have tools. You can solve this 3 different ways. You could, 1, use algebra and work your way through this, which we will in a second. You could, 2, use a graph and the intersection to find the solution. Or 3, you could use, put in your equation and use the table. So you actually have 3 different ways that you could pick to find the solution to this equation. Let's do it algebra first. So I'm going to follow the pattern from each one of this problem. Algebra, graph, table, and see if they all line up here. Okay, algebra. Well, my first instinct is to distribute. So 4x minus 8 plus 2x is equal to 12. 4 x's plus 2 x's makes 6 of them. 6 x's take away 8 is 10. Well, that means that 6x has to be 18 because 18 take away 8 is 10. So, okay, and if you're like, I use the additive property, go ahead, you add 8 to both sides. And then scale this down by 6, divide by 6. 6 times 3 equals 18. Okay, but then, so I feel like I have solved the equation, and it's true that you could take this and plug it in and make sure you're right, but a lot of people are pretty insecure about whether or not they did the steps, every step right? In order to solve an equation, you had to do every step with precision and accuracy, and sometimes we make mistakes. So I am going to go ahead and put this into the calculator. Okay. So that means into y1, I'm not putting that. I could have made a mistake on that. I'm going to put that. So clear this. I'm going to put 4 parentheses x take away 2 parentheses plus 2 times x. And into y2, I'm putting 10. Okay, so I just put the left side into y1, the right side into y2, and now I'm going to go zoom, and I'm going to go down to standard and have it graph. Okay, well, it looks like they meet, so I'm going to go ahead and do second calculate, intersection, and it did. And voila, we actually did our algebra right. They intersect at when x equals 3. Okay, so, whoops, where am I going? Where am I going? The graph looked a little bit like this. Whee. And whee. Yeah, to solve our equation. And then last, we could have also looked at the table. So second table. And okay. Oh, there it is. 10, or the left side of the equals is equal to 10, the right side of the equals. So they're both equal when x equals 3. Okay, so if we want to make sure that our algebra is right, we could put this into y1, that into y2, and we could actually use our calculator to verify that we did it right. So just to jot this down, right, in this table, when x was 2, we had 4 and 10. When x was 3, we had 10 and 10, giving us equals. That's when we know we can stop and know that our answer is x equals 3 to give us equality. And the next value, okay. Voila! So now we can solve equations like this using our calculator too. And we can also solve equations like this. Yay! Okay. Right on. So, first things first, we're going to do the algebra way. And then after that, we're just going to use one or the other for the calculator. So, 2/3, 1/6, and 1/4. Now, I am actually going to scale these all up. I'm going to scale them up by 12, actually, because I know that 12 divided by 3 is 4. I know that 12 divided by 6 is 2. And I know that 12 divided by 4 is 3. So I'm going to scale all of these up and multiply them by 12. So here we go. 12 times 2/3 x plus 1/6. Okay. So I am scaling up both sides of this equality because then it maintains equals. And scale 2/3 up by 3. If you multiply this, then you should get 8. Okay, so, and if you're like, what? So, you could think of this two different ways. 12 2/3 is actually 24/3 because you had 12 sets of this, and 24/3 is 8. Or you could think of this as, well, I took 1/3 of this 12 and that was 4, and 4 by 2 is 8. However you want to view it, whatever. But I also know that 12 sets of 1/6 is 12/6, which is 2. And 12/4 is actually 3. Okay, so I just scaled up both sides of this equal, and now it looks much better in terms of algebra. If 8x plus 2 equals 3, then 8x must be 1. And if I take a number and I scale it up by 8 to get 1, it must be an 1/8. Okay, so we did solve our equation, and now in order to do this on the calculator, here we go. I have to clear this out. And let's see. On the left side, so we have 2/3 x plus 1/6. And on the right side, we had 1/4. Got it. And we're going to get eighths, so we're going to get fractions. I'm going to go to my table, so I'm going to use my table instead of my graph. And let's see, can we find out where they're equal? Somewhere between 0 and 1. And now I'm going to go start at 0 and count up by maybe 0.05s again. Go back to the table. And let's see, did that work? No. Oh man. So back to the table set. And this didn't work, so 0.01 maybe? And now I'm going to go second table again. And let's see. No, not good enough in terms of precision. Boo. Okay, here we go. Let's see if the graph serves us better. We could have kept at it, by the way. Precision and persistence and precision. All right, whoa, look at that. Here we go. So second, calculate, go down to intersect, enter, first curve blue, second curve red, guess at 0, sure. Ah, there we go. X is 0.125. Okay, so we double checked this by doing y1 equals 2/3 x plus 1/6, y2 equals 1/4. The graph, very, very interestingly, looked something like, and I don't know, I couldn't make it any more precise than that, but they were very close together. And it said that x equals 0.125. And now you could be thinking, whoa, we got it wrong. But that's not the case. 1/8 and 0.125, those are equivalent. That's the same value, just written differently. Okay, find an x value that is not a solution to this equation. No. Go back to number 6. Because those look like the same problem, am I right? Let's see if we can line these up and see if they're identical problems. Yeah, they are, except this one said find the solution or solutions to this equation, and we did. But it says here, find one that's not. Well, look, 2 is not, 4 is not, because we didn't get the equals. So I can actually quickly use the table that I did in number 6 to find a non-solution. Namely, the first non-solution I'm going to say is, well, when x equals 2, we have 4 equals 10, which is false, or which is not equal. Yeah? And we use, and see table in number 6. Make sure you reference where you did your work, because we will always be looking for the work. But we could have also plugged this in and seen that, 2 take away 2 is 0, 4 times 0 is 0, and 2 by 2 is 4. So 4 equals 10. Nope. No can do. And then it says use the graph to find the solution. Ooh, but we already did that. We actually did that right here. But then it says also to find the solution to this equation equals 28. Okay, so back to what we had done here. Okay, so in number 9, all of a sudden, instead of using the graph to equal 10, we would keep a similar thing into y1, but now y2, instead of being 10, is 28. Ah, okay, so there's actually kind of a perk to doing this calculator business. A little bit of a perk is, all right, what was our equation? 4 times the quantity x minus 2 plus 2 x's. And now, if I wanted to solve this equation for many things at once, like first we did 10, but now we're doing 28, all I would be doing is changing this y2. So that's kind of convenient. That's nice. Let's see. I vaguely remember that we had to zoom out, but I'll graph it again and see what happens. Did we have to zoom out? Here we go. Let's zoom out. All right, now we can find the intersection. So, second, calculate the intersection point. First curve is blue, second curve is red, and voila, it has found our solution, x equals 6. Okay, so similarly, and this intersection point right here is at x equals 6. Okay, and just so that we feel comfortable with that, I'm just going to do a quick check before we make some remarks about this. So 4 times 6 minus 2 plus 2 times 6. Okay, so I'm plugging this value of x equals 6 into the left side of the equals. Well, 6 minus 2 is 4. And that reads, so 4 times 4 is 16, plus 2 by 6 is 12, and 16 plus 12 really is 28. So it really does check out. Nice. Okay, let's see what we got here. I can honestly say that definitely have to talk about these calculators. Okay. So my first remark when it comes to this is that scenarios have an explanatory variable, which we input, and a response variable, which we output. So let's not forget that. So even as we move towards these abstract constructs, let's not forget all of these are founded in real situations. So scenarios have an explanatory variable. Usually, okay, sometimes they're related, but we don't know which is explaining which. And by the way, this is sometimes called the independent